Hello students. So in this video we are going to study all about the Ampere's Circuital Law. Let us study by comparing it with what we have studied previously in electrostatics. So in electrostatics we have Gauss law, that is an alternative form of Coulomb's law. What we have in electrostatics, when we have studied electrostatics, we found that we have Gauss law as an alternative to Coulomb's law. Similarly, here when we are studying magnetostatics or about the magnetic field, we have Ampere Circuited Law as an alternative form of Biot-Savart law. What we have in magnetostatic, we have Ampere's Circuital law as an alternative form of Biot-Savart law. So we can also use Ampere Circuital law at the places where we use Biot-Savart law. So let's talk about the law कि है क्या इसमें. So basically Ampere Circuital law gives a relationship between the line integral of magnetic field B and the total current capital I which produces this field. We have studied that there is a current carrying conductor. If there is a current carrying conductor, then a magnetic field set up around it because of the current flowing through it. So the reason for the magnetic field set up around any conductor is the flow of current, and this Ampere Circuital law gives the relationship between that current as well as the line integral of the magnetic field capital B that is set up because of that current only. Alright, so let's see the statement of this law. So Ampere Circuital law states that the line integral of the magnetic field, we can write it as the line integral of magnetic field capital B vector around any closed circuit is equal to the mu naught. Now mu naught is the permeability of that medium surrounding that conductor or the circuit. So this magnetic field B vector around any closed circuit is equal to the mu naught times the total current capital I passing through that closed circuit, passing through this closed circuit. So what this Ampere Circuital law states that the line integral of magnetic field B vector around any closed circuit is equal to mu naught times the total current capital I passing through this closed circuit, right? So we can write it mathematically as, if we want to write in mathematical form, we can write it as the line integral of V vector for a closed circuit. Now this represents that the integration is happening over a closed circuit is equal to the mu naught times of the total current I passing through that circuit or flowing across that closed circuit. This is the mathematical form of Ampere Circuital law that we can use instead of Biot-Savart law. So in simplified form we can state it as, if a field capital B vector is directed along the tangent to every point on the length or the perimeter capital L of a closed curve, and its magnitude is constant along that curve, then BL is equal to mu naught capital I. Now this is the relation when if we state this law in the form like this, when the field B vector is directed along the tangent to every point on the perimeter or the total length perimeter capital L of the closed curve that we have considered, and its magnitude is constant, then now this magnitude is constant throughout the curve, along the curve, then in that case we can write this law as BL is equal to mu naught I, when the field B vector is directed along the tangent to every point on the perimeter capital L of the closed curve, and the magnitude of this field is constant along the curve, then we can write the relation, this line integral can be written as BL is equal to mu naught I. This is the more simplified form of Ampere Circuital Law, where capital I is the net current enclosed by that closed circuit. So capital I is the net current enclosed by that closed circuit. Circuit must be closed for applying Ampere Circuital Law. It is necessary. Now the closed curve where we can apply this Ampere law is also called Amperian loop. What we call it as the loop or the circuit where we can apply Ampere Circuital Law is called Amperian loop, because Ampere Circuital Law is valid in that circuit or loop, then we called it as Amperian loop. Alright, so this is the Ampere Circuital Law, which states that the line integral of the field B vector around any closed circuit is equal to the mu naught times the total current capital I passing through the closed circuit, and mathematically we can write it as closed integral of B dot dl is equal to mu naught I. This is the Ampere Circuital Law. Now we can prove this law for a straight current carrying conductor. For proving this law, we are going to take a straight current carrying conductor and find the result. So now we are going to prove Ampere Circuital Law for a straight current carrying conductor. This can be done as, so for this we are going to consider an infinitely long straight current carrying conductor and current flowing through it, let that current be capital I. Now we will use the Biot-Savart Law first to find the result. So what we are doing, we are taking a infinitely long straight current carrying conductor, like as I am going to show in the diagram. So according to the diagram, we have an infinite long straight current carrying conductor with capital I current flowing through it, and we want to find the magnetic field capital B at a point at the distance r from this wire. So at this point we want to find magnetic field B because of this conductor, and we are going to use first Biot-Savart Law for this. So according to Biot-Savart Law, this magnetic field at this point at a distance r from this conductor is given as B is equal to mu naught I upon 2 pi r. This result we have already derived in the previous video, where we get the answer in terms of phi 1 and phi 2 for a long straight infinite wire, and for infinite wire this phi 1 and phi 2 will become 90 degree. So by applying this, we can find the result B is equal to mu naught I upon 2 pi r using Biot-Savart law for a straight current carrying conductor. Now, the field B vector is directed along the circumference of the circle of radius r with the wire at its center, right? And the magnitude of the field B vector is same for all the points on the circle. If we take any point on this circle of radius r, then the distance will remain same r, so the magnitude of the field B will remain same at all the points on this circle of radius r, and the direction of B vector is always directed along the tangent taking across the circumference of the circle. Now, to evaluate the line integral of the magnetic field along this circle, we consider a small current element dl vector along that circle. As we are proving Ampere Circuital Law, so we want to find the line integral of magnetic field. For that, we are going to consider a small current element dl vector here, a small current element dl vector along the circle. Now at every point on the circle, both B vector and dl vector are tangential to the circle, so the angle between B vector and dl vector is always 0. If we consider any other point, suppose I am going to consider element here, right? Suppose this is dl vector, then the direction for magnetic field is also along the tangent here, and the distance is r. So the angle between B vector and dl vector is always going to be 0 degree. We can find B vector dot dl vector for this. So always for any point on that circle of radius r, B vector dot dl vector will be equal to B dl cos 0, and cos 0 is equal to 1, so B dot dl is equal to B dl. Now this is the dot product of B vector and dl vector. Now we are going to find the line integral of magnetic field along this circular path. So line integral of magnetic field means B along the circular path this will be closed integral of B dot dl. Now this is equal to B dot dl we have already find is equal to B dl, alright, and the magnetic field B is constant, so we can write it as B closed integral of dl. Now closed integral of dl shows that the line integral of dl over the loop, over this closed circuit or the circle, so this will be equal to the whole length of this circle, and the whole length of the circle is actually the circumference of this circle. The whole length is actually the circumference of this circle of radius r. So we can write it as B into 2 pi r, which is the integral of this dl. dl का integral हो जाएगा total length of the circle, and the total length of the circle is actually the circumference of that circle, and the value of B, we know that the value of B is mu naught I upon 2 pi r, so we can put it here, mu naught I upon 2 pi r into 2 pi r. So on solving this, we get closed integral of B dot dl over the length is equal to mu naught I, which is actually the required relation that we known as Ampere Circuital Law. So this law is valid for any assembly of current and for any arbitrary closed loop. Here we prove this law for a straight current carrying conductor. Now for how we did that, for a straight current carrying conductor using Biot-Savart law, we know that B is equal to mu naught I upon 2 pi r. We put phi 1 and phi 2 is equal to 90 degree, right, in the formula for a straight current carrying conductor. To make it of infinite length, we put phi 1 and phi 2 is equal to 90 degree. Then from the figure we can see that the direction of dl vector element and the B vector is always along the tangent at that point, and the direction of dl vector and B vector are same, so the angle between them is 0 degree. So we find B dot dl as B dl cos 0 or B dl cos 0 is equal to 1. Then we find the line integral of B dot dl that we have to prove in Ampere Circuited Law. So what we get, B constant and integral of dl over the closed circuit, and this integral is actually equal to the whole length of the circuit, and in this case whole length of the circuit is equal to the circumference of this circle. So B, this line integral is equal to B into 2 pi r, and we substitute the value of B from here. On solving this, we get closed integral of B dot dl is equal to mu naught times of current flowing through the conductor. Now this proves the Ampere's Circuital Law, and this law is valid for any assembly of current and for any arbitrary closed loop. So this was all about the Ampere Circuital Law. I'll come with the next video soon. Till then, stay tuned and study hard. Thank you.